covers some very practical issues that can improve the smoothness performance of your paving crews. So why is smoothness needed? There's plenty of research showing that smoother roads last longer and require less maintenance. And that makes great sense because bumps cause variable loading conditions from traffic and increased fatigue on the road structure. So a road that lasts longer is more valuable and saves tax money for the years to come. Depending on the country and state you're in, agencies will pay more money for smoother roads and in some cases will penalize us if the roads are not smooth enough. Smoothness starts with the first lift, or in the case of mill and fill projects, smoothness starts with the milling. Smoothness is not a topic only for the final lift. Each lift, including milling, is an opportunity to improve smoothness. It is just not possible to start with an existing road that scores 150 on IRI and achieve a score of 30 after one lift. But as an example, you could get well below 100 after the first lift, down to the 50s after the second lift, and down to the 30s on the third lift. The final paved surface smoothness is affected and limited by the quality of work of the earlier paving lifts and of the milling operation. One very practical way to improve the final smoothness of a project is to get the correct profile or cross slope built into the surface during the first pass. I will talk about this a little bit more in a little while on some other slides. Both milling and paving, the fundamentals are critical for good performance. The automation on the paver cannot make up for poor paving fundamentals. They will try to do so, and the automation will sometimes get blamed when the problem is actually something else. For example, if the auger controls are not set properly to maintain a constant head of material and the screed is reacting this, the automation will sense this and try to compensate. But it is not able to respond quickly enough to counteract the effects, and it could even appear that the automation is not performing properly, when it actually is not the root cause of the problem. It is not in the scope of this presentation to go through each of these items in great detail, but what we want to emphasize on is that applying best practices in the screed adjustments, the auger feeder system, and the head of material, and so on, is pretty exquisite to achieving smoothness. The screed is pulled along from the toe point and is free floating over the asphalt, pathing underneath it. The screed will react to poor paving practices. For smooth paving, we want to keep the screed from reacting to poor paving practices and allow the automation to control the screed relative to external references. Changes in paving speed affects the shear factor or resistance felt by the screed, causing it to rise or fall. Again, the automation cannot react quickly enough to compensate for this. The amount of rise or fall, of course, depends upon the magnitude of the speed change. The best practice is to pave continuously at a steady speed. This is also called balanced production. To accomplish this, we need truck capacity and a steady supply of HMA from the plant. For the paving crew, the key factor is setting a paving speed that matches HMA delivery based on the paving width and thickness. Thirdly, we need to have the roller capacity to achieve proper compaction while keeping pace with the paver and operating in the right temperature zone. There's certainly a lot of variables, but continuous paving will yield smooth paving. The main variable under the control of the paving crew is paving speed. Most lengthy paver stops are caused by paving too fast. Paver arm measures and records the thermal profile of the entire mat and also the paving speed. With this information, paver arm also logs the duration and location of paver stops as well as any temperature segregation. With a smoothness measurement report, you can find the actual bumps that are caused by paver stops. A quality assurance system like paver R does not solve the problem of paver stops and segregation by itself, but it does help identify the problem and find the causes, and is a valuable tool for a quality-minded contractor. The automatics or grade and slope controls, they are also called, are the system on a paver or mill that makes a measurement relative to an external reference, compares the measurement to a set point value, and then makes an appropriate signal to the valve to raise or lower the toe point cylinder. This changes the angle attack on the screed, which brings the screed back to the point where the sensor measurement will match the set point. This is a real-time control loop that is continuously measuring and correcting. The grade and slope controller uses sophisticated algorithms to maintain smoothness while maintaining the correct grade and cross slope. In practical terms, the controllers are continuously making small corrections to even out any transitions and leave the smoothest mat possible while also maintaining the elevation and cross slope set points. Grade and slope control interfaces to the paver via the hydraulic valve that controls the toe point. For the best system performance, this interface needs to be very precise. In other words, the controller output needs to be calibrated to the individual valve. Each valve will be slightly different, and a poor valve calibration will result in poor smoothness performance. The valve calibration determines how toe point cylinder will react and how fast it will move to change the screed angle of attack. If the calibration is off, the system can either be over or underreactive, and in both cases, smoothness performance is compromised. The best practice is to follow the manufacturer's recommendations. This is not an everyday maintenance item, but should definitely be done at the beginning of the season or after grade and slope controller is replaced. It's also a great idea to check the valve calibration before starting a big project, with smoothness is a huge priority. As mentioned before, the screed is free floating over the mat underneath it. It is not like a blade or a mold or a drum, where the hydraulics directly control the position of the tool. When we manually adjust the toe point or when the automatics are making a correction, it takes traveling 6 toe arm lengths to see the full change. The screed naturally smooths out the change over distance. 2/3 of the change occur in the first toe arm length and 2/3 of the remaining in the second toe arm length, and so on. The point is we need to let the automatics and the screed do their job and not expect an immediate change. In the case of checking thickness, as you can see in the picture. For smoothness, as immediate change is exactly what we do not want to see. This diagram just makes this point graphically and shows the screed reaction to a change in the toe point over the 6 toe arm length of travel. Independent of the brand of the grade and slope controls, there will be a number of options or settings that can tune the performance of the system. We already talked about the valve calibration, but there are a number of other parameters as well, such as sensitivity, working window, sensor selection, etc. Only trained crew members should be accessing these. Any change that is made can just as easily make the system perform worse. Only someone who knows that what they're doing should be looking at these. The second point is stick to the manufacturer's recommendations and guidelines. Having said that, this is something that should be checked routinely, and especially when it doesn't seem to be performing quite right. Grade sensor mounting is very important. An ultrasonic sensor is using reflected sound waves to measure the distance to grade. And because the speed of sound in air is affected by temperature, sudden changes in air temperatures will adversely affect the accuracy of the measurement. The sensors compensate for this, but it's still the best practice to mount the sensor a bit closer to grade than the maximum range would allow. 14 inches is the optimal height, and of course the sensor needs to be measuring over a good clean reference, because this reference is what the controls will match. Another key point with grade sensor mounting is how far forward or back the sensor is placed. Based on geometry, a sensor mounted near the augers will be more reactive, and a sensor mounted closer to the toe point will be less reactive. For best smoothness performance, the best practice is mounting the sensor at or just behind the toe point. Slope control presents a number of issues. When we are paving with slope control, the yield will depend on the profile of the existing surface, and the depth may vary across the width of the mat. Typically, smoothness is measured in the right wheel path and the left wheel path. The data tells us that the wheel path on the side using slope control will not have as good as a smoothness score as the grade side. Achieving the correct cross slope, yield, and also smoothness is a big challenge. Super elevations, where the cross slope is changing, coming in and out of the turns, is especially challenging. The best practice for slope control is building the correct cross slope into the pavement in the first lift or during milling. If this can be accomplished, paving great grade on the subsequent lifts and with averaging skis, if possible, will maximize the smoothness result. Some inspectors might want to see the percent slope and the control slope on the control box, but hopefully you can show the inspector that if the correct cross slope already exists from the previous lifts, paving great grade will both maintain the correct cross slope and maximize smoothness. Best practice with grade and slope controls for achieving smoothness is using an averaging ski. There are several types available, including ultrasonic, non-contact skis, and a number of mechanical ski options. This is the best tool for smoothness, and dual averaging or averaging skis on both sides is ideal. Even when matching a joint, an averaging ski yields the best smoothness results. In conclusion, there are three main themes for achieving the best smoothness performance. First, understanding the paving fundamentals is foundational. Second, continuous paving is smooth paving. And finally, the proper use of the automation is critical. Thank you for your interest, and please contact us for any further questions.